A new understanding of the mechanism of geomagnetism has been suggested by Auroras. Hints to elucidate the mechanism of geomagnetism can be obtained from Auroras. The swaying of Auroras suggests that the Sun's activity is related to the geomagnetism. The proton H+ of the solar wind reaches Earth's atmosphere at high speed, but the mean free path rapidly is decreased at under altitude of 100 km, so it does not reach to the ground. The aurora is observed at night, and it is weak at daytime. The auroras on the daytime hemisphere are observed at latitudes of around 75 degrees, and around 65 degrees on the night side. It may be due to the neutralization of the positive ions of plasma from the Sun, because there are many free electrons generated by X-rays and ultraviolet rays from the Sun on the daytime hemisphere side. When the solar wind enters the Earth's polar region, the positive ions inside the magnetosphere offset by free electrons, and only charged particles along the outside of the magnetosphere will enter to the atmosphere. The magnetism is generated by the motion of charged particles flowing through the closed circuit. However, the action of magnetism exists even in the motion of charged particles which are not closed circuits. It creates a vector potential in which the handling particles that are in motion. There is a relationship that magnetic flux density B can be obtained line integral of vector potential A. The magnetic field for the motion v of the charged particles Q becomes weaker when moving away from the charged particles. The energy of a charged particle q at speed of v in the vector potential A is given by eq.1. Charged particles moving in the same direction are arranged in parallel to reduce magnetic energy. In many particle systems, conflicting internal forces are offset when combined. In addition, the magnetic field due to the motion of the point charge becomes weaker when it leaves the source. Therefore, there are many elements of geomagnetism in areas where there are many high-speed charged particles. When the charged particles are high-speed, the magnetic action becomes stronger. In high-speed charged particles running side by side, if the polarity is the same particles, they attract each other as parallel currents, and when the polarity is different, they repel as anti-parallel currents. The Earth has Van Allen radiation belt, which consists of outer belt, slot region and inner belt. In addition, there is another slot region between the inner belt and ionosphere. Such layered structure is formed by high-speed charged particles. In the polar region where charged particles gather, positive ions and free electrons are offset by the proximity. The remaining charged particles in the outside of magnetosphere enter the ground perpendicularly together with the magnetic field. The region with the weakest magnetic field strength on the surface is the South Atlantic, with the southern end of the inner belt in the sky. Earth's equatorial radius r is 6,378 km, and the electron density of the ionosphere is about the 12th power of 10 for 1 cubic meter at the altitude of 300 km. There are positive ions of oxygen O+ at similar concentrations in this region. Positive hydrogen ions H+ escape from the Earth's gravity, so they are less than positive ions of oxygen. The electron-dense ionosphere rotates counterclockwise in the Earth's rotation to create geomagnetism of the Earth. The current orbits the clockwise lode, and the magnetic field line goes from the South Pole to the North Pole, invading the Earth's interior in an area a little far from the axis, which is the pole of geomagnetism. The strength of geomagnetism on Earth is weak at the equator and strong in high latitudes. Its value is in the range from 24,000 nanotsla to 66,000 nanotsla. These values are very large compared to the calculated value of the magnetic field on the surface of the Earth by the motion of charged particles responsible for geomagnetism in the sky. Therefore, we think as follows: the motion of charged particles in the upper atmosphere induces an electric current on the Earth's surface, and the current in the Earth's surface has large influences on geomagnetic measurements. Jupiter and Saturn are covered with hydrogen. Hydrogen ions of the solar wind invade, and the atmosphere containing many positive ions rotates in the direction of rotation. Therefore, since the geomagnetism of Jupiter and Venus rotates counterclockwise due to rotation of the current by hydrogen ions having polarity opposite to electrons, the geomagnetism is headed from the North Pole to the South Pole. Hydrogen ions in the solar wind also create an anti-clockwise microscopic magnetosphere in the vicinity of each charged particle. It is in the same counterclockwise direction as Jupiter's geomagnetism. The microscopic magnetosphere goes to the Arctic area where magnetic lines become denser, and the magnetic potential energy becomes lower. On the other hand, because electrons are negative in polarity, they move to the Antarcticas in the opposite direction to Jupiter's geomagnetism. Therefore, Jupiter's auroras occur only in the Arctic region. The orbital velocity of Jupiter's magnetosphere in Io's orbit is 74 km per second. Io, on the other hand, orbits Jupiter at a speed of 17 km/sec. Therefore, hydrogen ions of the solar wind captured in the magnetosphere of Jupiter are swept at 57 km/sec. The kinetic energy corresponds to 17 electron volts. The collision of H+ ions captured in Jupiter's magnetosphere sputters the surface of Io and releases plasma in the direction Io is moving. It has been observed that Io at the evening side where the solar wind is received by the headwind is bright, and it is dark on the morning side received by the tailwind. Since the plasma torus of this satellite orbits at 74 km/sec, it forms a magnetosphere. Jupiter is orbiting at a high speed of about 10 hours and has strong geomagnetism. However, the orbit of Callisto is farther away than the other three Galileo moons, so it is outside of Jupiter's main radiation belt and is less affected by it. The charged particles sputtered by the sweep of Jupiter's magnetosphere will orbit along each orbit. So, each satellite has a magnetosphere by the orbiting charged particles. Since the charged particles running outer region of the magnetosphere on each satellite create auroras in Jupiter's polar region, the glow point of the charged particles in the magnetosphere of the Moon away from Jupiter is close to Jupiter's geomagnetic pole. Auroras suggest a mechanism of geomagnetism. It can be explained by thinking about the motion of charged particles. Quantitative verification is a future issue. Thank you so much for listening.